a lead coefficient test. I need to know, is it going up? Is it going down? Is it doing this? Is it going like this? So I want to look at the very first term that would be possible. Well, the first term, or the highest power we would possibly have is, well, this is x to the fifth. This would be x to the first, and this would be x squared. So our biggest power would be 2 plus 1 plus 5, which would be x to the eighth, but we have a small thing we have to take care of. This would be a positive times a negative times a positive. That would give me a negative x to the eighth. So maybe we're okay. Maybe we're okay. So we'd have negative x to the eighth plus something, something, something. I don't care what the other somethings are. Well, it's negative x to the eighth, which means that I know what's happening at the two ends. So our two ends, let's help me out here. So we're over here. Am I going to start high or am I going to start low? What am I doing, high or low? High or low? High or low? High or low? Low. I'm going to start low. And since it's even, both of ours go the same direction, so I'm also going to end low. Now I just need to know what happens inside of here. So we have to look at our zeros. So one of our zeros is going to be x equals 2. What's the multiplicity on that?
5.
I have x equals 2. What's the multiplicity on that? 5. So it has a multiplicity of 5. What happens when it's odd multiplicity? Does it cross or does it bounce? Cross or bounce? Brian?
It crosses.
It crosses. So we're going to cross at 2. Then we have, our other one will be x equals 3. That is going to be a multiplicity of 1. That is also going to cross. Then finally we have x equals a negative 1. That is going to have a multiplicity of 2. So it is going to bounce. All right, so our three zeros are negative 1, 3, and 2. So we should go ahead and mark those. So at negative 1, I have a 0. At 2, I have a 0. And at 3, I have a 0. So 1, 2, I have a 0. And 3, I also have a 0. So we're starting low, and we're going towards negative 1. Well, it says at negative 1, it should bounce off. So we get close to negative 1, we're going to hit it, and we're going to bounce off. Then we're going to get drawn to 2. At 2, it's going to cross. Then it's going to come back to 3. 3, it also crosses. Yoinks. And it's going to look something like that. All right, now it's asking when is it less than 0? Remember, less than 0 is anything where y is less than 0. That's everything down here. Up here is where y is positive. That's where it's bigger than 0. So I'm looking at all the stuff down here. Well, on our graph, that's all of this. It's all of this. And it's all of this. Before I do anything, I'm going to look at that less than sign. There's no equal to on it, so you have to use parentheses on everything. No equal to sign means you have to use parentheses on everything. Do we use our x or y values to say what's going on? Yeah.
X values.
X values. When's the only time we use y values? When's the only time we use y values? Range. Range is the only time. So we're going to use our x values. So our x values would go from negative infinity all the way to, well, negative 1. But we can actually union that. I should have actually made that a little bit. Yeah, so I did make a mistake up there. So it would be negative infinity to negative 1. Union that with negative 1 to 2. And union that with 3 to infinity. So I did mess up on that one. But this would have been the closest one. So this we should have been negative 1 and 2. And that would be our correct answer. All right, questions on that? Okay, questions from the homework. Yeah, Grace.
I
All right, number 11. Number 11 says, write a polynomial inequality with a solution set of -1 union 2 union 3 infinity. So let's go ahead and write that down. So I have to have some kind of polynomial where our answer is -1. It has to be union with 2, and that has to union with 3 to infinity. All right, so let's think about that. There must be an equal sign to this. It either needs to be greater than or equal to or less than or equal to, because these are specific zeros. These aren't ranges. What it's saying is it hits that -1 and then it bounces off. And -1 happens to be a solution. And then it says 2 is a solution, and then it must bounce off from there. And then it says from 3 to infinity is going to be 0. So there's kind of two ways to do this. So let's start with the positive direction. Let's say, so I know that we have 3 zeros. We have a 0 at -1. I have a 0 at 2. And I have a 0 at 3. That's way too far for 3. I have a 0 at 3. All right, those are telling my zeros. Now, at -1, what needs to happen is it needs to bounce, because it's just that one value. If it cuts through, then it's going to be a series of values throughout there. So let's just kind of draw this graph. Let's just say, okay, it hits -1 there, and it bounces off. Then it hits -2, and it bounces off. And then it's going to cut through here. Bless you. So I want this to be included in the answer. So I'm looking at where y is less than or equal to 0. I'm looking at where y is less than or equal to 0 because I want to include the -1, I want to include the -2, and I want to include all of this. So my end answer is going to be less than or equal to 0. I want all of this and below. Well, in order for something to bounce off, it has to be an even power. It has to be an even power. So I need an even, odd. And since I know the zeros, I know the factor I could pull out. So we could look at x plus 1. X plus 1 gives me a 0 of -1. Well, it's got to be even, so it bounces there, so I'll make it squared. Then we need it to bounce at x minus 2 to give us that 2. Also even, so let's make it squared. And our final one needs to be odd, so I'm going to do x minus 3 to the first, to the third, to the fifth, to the ninth, to the 101st. It doesn't matter as long as you have an even here, and an odd here. And this is our answer. If you would graph this equation, it would look similar to this. These might go higher and stuff. And in fact, you could have this to any degree that's even. This could be x plus 1 to the 8th. This could be x minus 2 to the 10th, x minus 3 to the 121st. All right, so what you're really trying to do is get your zeros out, plot them, and then kind of draw what would match it, and then what you're looking for, either less than or greater than. Okay? Yeah?
Could you do that same graph and have it start low and high and have it be greater than you?
Mm-hmm. Absolutely. So what he's saying is basically, let's do this in purple. Purple will stand out. So we could also go the opposite direction, which would look something like this. In which case, we would have to flip that to a greater than or equal to 0. But same answer. All right, other questions? Leo. 6. 6 is saying x squared plus 16x plus 24 is greater than 6x. Well, the big thing there is we don't really know how we're going to solve it for 6x. So what you're going to do is you're going to move that 6x to the other side. So it's going to look something like this. So you're going to move that 6x to the other side so we can deal with 0, because that makes it easier. It makes it much easier to know I just want positives and negatives. So I move the 6x to the other side, which gives me 10x. This becomes factorable. And my zeros become -6 and -4. I did the test point method, but you could have also drawn a graph. Yes?
Wouldn't x plus 4 be x squared?
Wouldn't x plus 4.
Because you're moving the 6x over the other side.
Oh, yeah. So we have to move this -6x. That's what gave us that 10x.
Okay.
Yep. And now I can just look at 0. Now I can treat it like any other one. The easiest thing to do with polynomials is have a 0 on one side and everything on the other side. For anything you do, it's just easier. It leads you to the quadratic, factoring, completing the square. It just makes your life a lot easier. Okay. Other questions? Cool. All right. Then we are going to move on to rational functions. Rational functions were the ones where we had polynomials on top and bottom. That's where you did your vertical, horizontal, slant asymptotes, if you remember. They were kind of those weird graphs that made kind of C's and no, nothing. It happened. It happened. All right, a rational function is a function such that you have p of x over q of x, where p of x and q of x are both polynomials. So both of them are polynomials. Anytime we have a fraction, we should probably say something. What should we always say when we have a fraction? Liv.
Q of x cannot equal 0.
Q of x cannot equal 0. That was a bonus point, not on your last test, but the test before. You actually came up with an equation that had x's on the bottom, and if you just wrote, my denominator cannot be 0, that was worth 1 extra credit point. One person got it. All right, a quick example might be, I don't know, 3x over x squared plus 2. We have x's in the top, we have x's in the bottom. That's what makes it a polynomial. All right, we're going to start with the domain. Coming up with a specific domain for these different functions. So we are given the function 3 of x over x minus 1, and I need to find the domain of this guy. So the big thing is what's the one thing that I know can't be in my domain right now? What's the one number that can't be in this domain? 1 cannot be in this domain. 1 cannot be in this domain because this can't be 0. So when you're checking the domain, the first thing you're going to do is you're going to set your denominator equal to 0. Did I put denominator? Just put q of x. Yeah, let's put denominator. You got to set your denominator equal to 0. So in this case, we're going to set x minus 1 equal to 0. So that's going to mean that x cannot be 1. X cannot be 1 because your denominator cannot be 0. Are there any other limitations to this problem? Is this a square root problem? So picture a square root problem. Can you put negatives into a square root? No. So all you're asking for, are there any numbers that you can't plug into 3x? Is there any number you can't multiply by 3? Not imaginaries, but reals. So that works for anything. Is there anything you can't subtract 1 from? Not a trick question. Yeah, right. What was that? 1. 1's the only one that breaks our denominator. But is there any other number that breaks anything? No. So it's going to be all reals except for 1. So our domain is going to be all reals except 1. Our next one is find the domain of f of x equals 4 over x squared plus 1. So technically I can plug anything I want in for x squared plus 1, except where it equals 0, because that's going to make our denominator equal to 0. So the first thing we're going to do is we're going to look for things that make x squared plus 1 equal to 0. Well, if I subtract 1 from both sides, and then I take the square root, well, that just equals I. So is there any real numbers that I can't plug into it? It's saying I can't plug in I. Is I a real number? No, it's an imaginary number. So I'm allowed to plug any number I want in for this. There's nothing that I can plug into this to make this equal 0 except for imaginary number. And think about that. Any positive number plus 1 isn't going to equal 0. And if I plug a negative number in, if I plug in negative 1 squared is a positive 1 plus 1 is still a positive number. I can't get 0 out. So in this case, our domain would be all reals. Or you could write that as negative infinity to infinity. Whatever you want to plug in works. Let's look at this one real quick. So x minus 1, I could plug whatever I want. If I say f of x equals x minus 1, I could plug any number in the world I want in for it. The only problem is that it's a denominator. So it can't be 0. So something special happens at a number that you plug in and make your denominator 0. Something happens specifically on your graph. And that is a vertical asymptote or a hole. A vertical asymptote or a hole happens, and it's located at any value of x that makes your denominator equal to 0. So we're doing the same thing as the check before. We're looking at what makes our denominator 0. If it makes the denominator 0, it is either a hole or a vertical asymptote, and you're going to know after these two things whether it's a hole or a vertical asymptote. So we're supposed to locate the vertical asymptotes of x over x squared plus 6x plus 5. Vertical asymptotes are setting your denominator equal to 0. So to locate our vertical asymptote, we are going to set our denominator equal to 0. So we're going to go x squared plus 6x plus 5 equals 0. Now, hopefully this is factorable. It sure looks like it is, because 5 times 1 is 6 when you add it up. So we're going to factor this into x. X equals 0. Well, 5 and 1 are the only things that multiply to give them 5. Well, plus 5 and plus 1 equals 6. So we have two zeros. We have a 0 at x equals negative 5, and we have a 0 at x equals a negative 1. That means you have two vertical asymptotes. Your vertical asymptotes they're very excited for vertical asymptotes. I don't know why you guys aren't. They're not even in the classroom and they're excited about it. So you have two vertical asymptotes. Here's your two vertical asymptotes. You have a vertical asymptote at x equals negative 5 and x equals a negative 1. Note, these aren't points. These are entire lines. So it's the equation x equals negative 5. You would draw a dashed line. At x equals negative 1, if we were graphing this, we would draw a dashed line. We'll start doing that on the next side. But for right now, just picture I have two vertical lines that are vertical asymptotes. Those are important. Vertical asymptotes are important because your graph does something specific near vertical asymptotes. What it does is it gets very, very close, but doesn't touch it. That's what a vertical asymptote is. All right, the last one we're going to do is we're going to find the vertical asymptotes of x plus 3 times x minus 3 and x minus 3 and x plus 1. Note, we have two zeros. We have a 0 at x equals 3 and x equals negative 1. So our zeros Our denominator is zeros. Maybe I should set that up. We set up our denominator. That would be x minus 3. And x plus 1 equals 0. We would have a 0 at x equals 3. And x equals negative 1. This time, those are not both vertical asymptotes. X equals negative 1 will be a vertical asymptote. X equals 3 is not a vertical asymptote. And how you know that? Let's look what's happening here. So you have x minus 3 and an x minus 3 right here. Well, they would cancel each other out. Well, you can't plug in 3 to this equation. So what's going to happen here is if you ever have the same factor on the top as in the bottom, that is going to be a hole. Not a vertical asymptote, that is going to be a hole. So if you ever have the same factor in the numerator and the denominator, that's a hole and not a vertical asymptote. Negative 1 is a vertical asymptote because it isn't a factor on top and bottom. They wouldn't end up canceling out. So if they cancel out, it's a hole. If they don't, you have a vertical asymptote. So we have two things. We have a vertical asymptote. Let's just call it V dot A at x equals that negative 1. And we have a hole at x equals 3. So it would actually be a point. That would actually be a point. Don't forget about this fact, that you could have a hole or a vertical asymptote. All right, so that's our vertical asymptotes. Those are our holes. Let's go on to our horizontal asymptote. So rational functions, generally speaking, have a vertical and a horizontal asymptote. For horizontal asymptotes, we're going to remember the saying, Bobo Botten eats DC. Once again, Bobo Botten eats DC. Don't worry, on Monday there's a picture of Bobo Botten eating DC. So stay tuned for that. It's going to be fun. He's eating the whole city. All right, let's go to Bobo. Bobo, these are all talking about powers. The powers of your numerator and your powers of your denominator. You're looking at the biggest power there is on each of them. If it is bigger on bottom, your horizontal asymptote is 0. In other words, y equals 0. Bobo's kind of stupid. He just says, when you're in Bobo, you just go 0. Takes no work. Bobo, 0. Bigger on bottom, 0. Our next one is Botten. That is bigger on top. That is none. That is actually the most complex one. Because there is no horizontal asymptote, that means you are going to have a slant asymptote, which we're going to learn on Monday how to calculate. So if it's bigger on top, we have to wait till Monday to really do it. All right, next one is eats DC. That is exponents are the same, divide coefficients. Exponents are the same, divide coefficients. So exponents are the same, divide coefficients. So you're going to divide your lead coefficient. You're going to divide your lead coefficient, and that will tell you where your horizontal asymptotes are. All right, for A and B, how much time do we have? I feel like we're running over, but we're okay. All right. We're supposed to find our vertical and horizontal asymptotes of each function. So we have 2x squared over x squared minus 1. So let's go ahead and find our vertical asymptotes first. Vertical asymptotes. Vertical asymptotes are where we set our denominator equal to 0. So we'll go x squared minus 1 equals 0. Well, that's going to give me x squared equals 1. We're going to end up with x equaling positive or negative 1. So we have vertical asymptotes at x equals 1 and x equals negative 1. We'll graph that for the next problem. For right now, just kind of picture. We have a dashed line at 1, and we have a dashed line at negative 1. Now we're going to do our horizontal asymptote. Our horizontal asymptote. We are looking at the biggest power in our numerator and biggest power in our denominator. Biggest power here is 2. Biggest power here is there. So we have the same. They have the exact same power. So that's going to be same degree. That is going to be exponents are the same. Divide your coefficients. So that's going to be our eats DC. We have x squared and x squared. So we are going to eat DC, which we are just going to divide our lead coefficient. So our horizontal asymptote is going to be y equals 2 over 1, which is just y equals 2. That's our horizontal asymptote. Lead coefficient divided by lead coefficient is 2 over 1. All right, next one we have x squared plus x minus 1. What I always do is I write this in its factored form right off the bat to see if we can do it. So I'd write my denominator as 2 factors, and then look to see if I can do our numerator as factors too. So I go ahead and factor everything right off the bat. All right, so we have x, 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 x. All right, our bottom one, I need 2 numbers that multiply together to give me 6, but the difference is 1, so that must be 3 and 2. One of them needs to be negative, and it's got to be the 3, because negative 3 plus 2 is then negative 1. All right, on top, I only have 2 possible numbers that multiply together to give me 1. I need it to be multiplied to be negative. Is that one going to work? Is that one even factorable? No. Why might I check to see if it's factorable? Yeah, to check for holes. If it's not factorable, it definitely can't be x minus 3 over x plus 2. So these must actually be our, so this is not factorable. So we would just say not factorable, so we would just have x squared plus x minus 1. Always check to see if your numerator is factorable. That's the only way you can check for holes. All right, so there's no holes, so we'll check for our vertical asymptote. Check for our vertical asymptote, we're going to set our denominator equal to 0, so we have x minus 3 times x plus 2 equal to 0. We have 2 vertical asymptotes. We have one at x equals 3 and x equals a negative 2. Horizontal asymptote. Our exponents are the same. It's x squared and x squared. So once again, it's eats DC. DC says divide coefficients. So we're going to have y equals, our lead coefficient is 1 over 1. We just have y equals 1. For these problems, that's all the big work you have to do. You have to just draw your vertical and horizontal asymptotes. Everything else is just picking some points to see where the graph actually lies. All right, for example 6, we have to make a big step. Now we have to sketch the graph. So we're supposed to sketch the graph of 3 over x minus 2. And then we're supposed to state the domain. All right, let's start with our vertical asymptote. Vertical asymptote is where our denominator equals 0. So we're going to go x minus 2 equals 0. That would be x equals 2. All right, I have a vertical asymptote at x equals 2. Now let's do our horizontal asymptote. This is x to the first. This one is x to the 0th. So is it bigger on top, bigger on bottom, or the same? Yeah,
Bigger on bottom.
it's bigger on bottom. That means it's Bobo. Bobo stupid. Bobo just goes y equals 0. No work required. If it's bigger on bottom, that's what you should look for on the test. Bigger on bottom, it's like, yes, I have no extra work. It's just y equals 0. This right here is a bulk of your work. We're just going to plot those lines, those two lines, and we're going to test a couple points, and we have ourselves a graph. So let's make an x and y axes. That's perfectly straight, right? Good enough. Good enough for government work. All right. So we are going to label this. That's 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You should at least have something labeled so I know what scale we're at. All right, it says draw a vertical asymptote at x equals 2. A vertical asymptote is a vertical line at x equals 2. So I'm going to draw a nice dashed line. That's my x equals 2. Then it says draw a horizontal asymptote at y equals 0. Well, hopefully you can see this, but it's right at y equals 0. Do we see that purple line I'm drawing? Try to go a little further out. That would be my y equals 0. Now here's the cool thing. If we look here, we have two possibilities. Either our graph is up here or it's down here. Then I check over here. Either it's up here or it's down here. It can't be both, otherwise it wouldn't be a function. So we just have to check one point over here, one point over here, and we'll have our complete graph. Probably the easiest way to check on our left-hand side is just check 0. Plug in 0 into an equation, see if it's either up or there. So we're going to check a couple points. So let's go ahead and check g of 0. We'll check g of 0. So these are my vertical asymptotes. That's done. Let's check g of 0. So we're going to plug 0 into our equation. So that's 3 over 0 minus 2, which equals a negative 3 over 2. I really only care that it's below the x-axis. But we'll just plot 0, negative 3 over 2. 0, negative 3 over 2 would be about, let's go red. Here. That's enough for me to get a sketch. Our graph is going to look something like that. That's what asymptotes do. They prevent it from crossing, and you get really close to them. So this thing's drawn to both of our asymptotes, but it can't go through it, so it just gets really, really close and then stops. All right, let's check some point over here. Let's go ahead and check. Well, 2 wouldn't make sense to check because it doesn't work. Let's check 3. So let's check g of 3. Well, g of 3 would be 3 over 3 minus 2, which would equal 3 over 1, which just equals 3. So this would be the point 3, 3. Let's go out to 3 and plot 3, 3. Since it's up there, we know our graph's going to look something like this. That's our graph. We do our vertical and our horizontal asymptotes. We check a point at each section to see whether it's above or below our horizontal asymptote. And then we're done. It does ask us to state the domain. Can someone help me out with the domain? Liv?
All real numbers except 2.
All real numbers except 2. But x cannot equal 2. That's another way to do it instead of except. The other way you could have done it is you could have did negative infinity to 2 not including 2, union with 2 to infinity. Just let me know it's all real numbers except for that one. Somehow, some way. All right, questions on that? All right, that's it. Vertical, horizontal asymptotes. That is the meat and potatoes of graphing polynomial equations that are in fractions. Now, on Monday, we'll do some more rare cases. And actually, look at your homework really quick. Let's look at our homework really quick. Specifically because we still have more time. I don't know why people are packing up. All right. Let's look at... No, I don't think I have it on there. Never mind. You're good on this one. I put it on Monday's homework instead. All right, any questions on anything we covered? The homework should go really quick. I think it's only like 4 real big problems. The other ones are just finding domain of your rational function. You only really have to graph, looks like, what, 4 of them? That should be really easy. In fact, we still have a couple minutes. You'll probably get a couple of those done.